Good evening, everyone. Good evening. My name is Rocky Cobb, and I'll be chairing this evening's presentation. The American Physical Society works extra hard to bring physics to the public, and we're very happy to sponsor this public lecture this evening. And I would like to ask, actually the American Physical Society would like to know, who is here from the public who's not part of the meeting? Raise your hand, there's a door prize. Great. And two more questions. Who heard about it over the radio? Okay, I got that. And over social media? Okay, great. Thank you very much. Tonight's speaker is Katherine Freese. She is presently the George E. Uhlenbeck Professor of Physics at the University of Michigan. She's also a guest professor at Stockholm University, where she recently received a $13 million grant from the Swedish Research Council. She received 3 degrees in physics, a BA from Princeton University, an MA from Columbia, and a PhD from the University of Chicago. After postdoctoral research at the Harvard-Smithsonian Center for Astrophysics, the Kavli Institute for Theoretical Physics, and a presidential fellowship at the University of California, Berkeley, she joined the faculty of MIT before joining the University of Michigan faculty in 1992. This summer, she'll be moving from Ann Arbor to the University of Texas. She's had many visiting positions, including an important position as director of Nordida in Stockholm, Sweden. She's received many awards, including an honorary degree from the University of Stockholm. She's a fellow of the American Physical Society, and she is this year's winner of the Lilienfeld Prize of the American Physical Society. She has always been engaged in public outreach, giving many lectures. She has a book, The Cosmic Cocktail, 3 parts dark matter, and in the lecture today you will learn whether it is shaken or stirred. The book is available from Princeton University Press outside, and perhaps Katherine will sign a copy or 2. She's also given the Kavli Prize Lecture at the American Astronomical Society in 2017. She has worked on many areas of cosmology, including cosmic inflation and dark energy, and dark matter, the subject of this evening's lecture. She is the world's greatest cosmologist, according to her website. The subject of this evening's lecture is dark matter in the universe. Please join me in giving a warm welcome to Katherine Freese.
Well, thank you for that very nice introduction, Rocky. And I just wanted to clarify one thing. My website doesn't say anything about my being the world's greatest cosmologist. That would be Rocky on his website saying that he's the world's greatest cosmologist. Okay, we can duke it out later. So, in talking about the subject of the dark matter in the universe, I first wanted to reflect upon the amazing advances of the past 100 years in our understanding of the universe. Throughout history, starting with the ancients, people wanted to understand their surroundings. They wanted to understand what's out there, where did we come from, where are we going, and there were different creation myths for different cultures, for different eras. And as of 100 years ago, we have our creation myth. It's called the Hot Big Bang, but it's more than a myth, it's right. And it's not perfect, it's incomplete. We're working on many aspects that aren't explained, but the enormous advances are just mind-boggling. So I wanted to start with the one and only equation in this talk. Let's get it over with. But all of this started with the brilliant insight of Albert Einstein's relativity. And here are the equations. On the left-hand side, you have the geometry of the universe, the curvature. And on the right-hand side, you have all the content in the universe, the mass and energy. And you see an equal sign in between. And so, as a consequence of that, geometry is determined by matter content, or the other way around. And so the warping of space-time, for example, by the Earth is shown in this picture. And one of the reasons that I had to talk about this is because of this amazing discovery from a few days ago of the first time that a black hole has actually been imaged. Well, of course, you don't see the black hole. What you see is the light around it of gas that is swirling around the black hole before it gets sucked in. But that black part in the middle, that is the stuff that does not emit any light. So anything that goes in there will never come back. So this is a black hole that weighs 6.5 billion times as much as the sun, and all of that is squeezed into the size of the solar system. So this is just an incredibly cool result that I wanted to show you, and it took all these different telescopes around the world to turn the Earth basically into a single telescope. If you combine all the data from Hawaii, from Chile, from all over the world. And since right next door to this hotel, I don't know if you've been to Krispy Kreme across the street, but if you do, if you keep going, you'll actually get to a Potbelly's if you want a sandwich. But anyway, so I had to show this picture. So I do have to admit I'm a little off track here because supermassive black holes are not the dark matter. Every galaxy does have a black hole at the center, but all of that adds up to just a tiny fraction of the universe as a whole. So let me get back to cosmology. So starting again from Einstein's relativity from 1915, it wasn't much after that that other scientists applied those equations to the universe as a whole, making some very simple assumptions about what the universe might look like on large scales. They realized that you might have 3 different possible geometries for the universe, and the universe could be expanding, contracting, or static. Einstein liked the idea of a static universe. He liked the idea of this simplicity, the symmetry. But along came Hubble in 1929. He made measurements in the Mount Wilson Observatory in the Los Angeles Mountains above Pasadena. So I spent some time at Caltech about 5 years ago, and I looked at those mountains every day. You can see the telescope sticking out. And it's only when you try to bike up there that you understand. The vertical drop is the same as in Aspen. So, yeah, anyways, so using those telescopes, he first of all proved that galaxies existed beyond our own, because at the time of Einstein, people weren't sure if there was anything beyond the Milky Way. So it was only in the 1920s that that became clear. Things were just too far away. It couldn't all be in our galaxy. Then he also made another incredibly important contribution, which is he observed light from galaxies at various distances away from us and realized that the light that's emitted from those galaxies, we understand the emission very well, but that light was stretched between the time it was emitted and the time it gets to us. So as a pretty bad analogy, actually, if you drew on the surface of a balloon, you draw a wave, and then you blow up the balloon, you'll see that the wavelength gets longer, the wave is stretched, and that's what he saw. So the conclusion is that the universe is expanding. And at that point, Einstein had to abandon the static universe. So a very simple-minded picture, galaxies are moving apart from one another as the universe is expanding. So cosmologists believe that the universe started 14 billion years ago. Well, it's more than a belief. We understand the Big Bang, we understand when it happened, and the universe started out hot, and it's been cooling and expanding ever since. So I'm going to try this pointer here. I was afraid I'd never get it to work. It does work. So you have all kinds of particles, quarks, leptons, electrons, photons, all kinds of particles really tightly packed at the very earliest stages in the universe. And then as time goes on, these particles spread out. So Rocky, I think I stole this from you, didn't I? The primordial soup can. So one way of thinking about the expanding universe is with another simple analogy, the raisin bread model of the universe. So here you take a piece of dough with raisins in it and you stick it in the oven, and they tell me if you do that, because I don't cook much, that the dough rises and the raisins move apart from one another, which is kind of an analogy for what galaxies are doing due to the expansion of the universe. The only problem with the analogy is that the raisin bread has a center, but we don't think that the universe does. In fact, that thinking is built into the equations that we use to describe the universe. Okay, so now let's start from today's universe and go backwards in time. Let's go back towards the Big Bang, and if you do that, then everything gets closer and closer together, which means that everybody in this room would get packed, oh boy, into a single point. It's a pleasant thought. But if the universe is infinite, which is very possible, likely I guess, then things that are way out at infinity, no matter how far back you get, there will always still be something out at infinity. So the limitation that we face is when you try to squeeze things together too much, you reach a point where the laws of physics as we know them don't work. And so we're stuck by our lack of information how to go any farther back. That's the thing that we call the Big Bang. So the Big Bang is not the idea that things did not start at one point. So you can think of the Big Bang as a point in time rather than a point in space. And by the way, there's no explosion, but it makes for a good slide. So where do we stand in cosmology? Well, there were some big questions answered, certainly over the last 100 years, but even since the turn of the millennium. What is the geometry of the universe? What is the total mass and energy content of the universe? How old is the universe? We know the answers to these questions, but there are plenty of other things that we're working on. How did the universe begin, and what is it made of? I did want to say a few things about one of these amazing accomplishments, which is that we've figured out the geometry of the universe. So I mentioned that there were three possible shapes. You might have the universe living on something like the surface of a sphere, or it could be on a saddle, or it could be, well, sorry about these pictures, they're obviously lower dimensional analogs because I can't draw in 4 dimensions, but so the idea is that the geometry would be different, and this was the status in the 1930s. And it's this picture is fun. So if you had the flat geometry is the one you learn about in mathematics in middle school, where parallel lines never meet. Whereas if you had the other alternatives, you could have this guy here in a closed universe sending out 2 light beams. He thinks they're going out parallel, but they reconverge him and bite him from behind. So those were the 3 possibilities, and we now know what the answer is to this really sort of holy grail question. And it was found by looking at the leftover light from the Big Bang, which is called the cosmic microwave background. And this is a subject of its own, but I just wanted to say this is the sky. When we look out into the sky, this is what we see when we look in the microwave. So microwave light has hot spots in orange and cold spots in blue. And it's this, believe it or not, it's the size of the hot spots that tell us the shape and geometry of the universe. So the prediction was, if the geometry is flat, parallel lines never meeting, then the size of those hot spots should be about 1 degree. And sure enough, there it is, 1 degree. There the data is sticking out. So yes, the geometry is flat. And when I say flat, I just mean calculationally it's flat. It is, in fact, 3-dimensional. So if you take a cube, you would take each side out to infinity. But there's no curvature to the universe as a whole. Then that very first equation that I gave you on slide 1 tells you that the geometry is connected with the total mass and energy content. And now that we know the geometry, we know how much stuff is out there, and the answer is 10 to the minus 29 gram per cubic centimeter, comparing to water on Earth is 1 gram per cubic centimeter. So the outer space is really diffuse. And I tried to once explain this to the Queen of Sweden, and it was a how do you pronounce it, debacle. So it's a funny story, and I'll tell you if you want come up afterwards. But before I leave this data from the cosmic microwave background, I do have to show you, here we have the initials SH, Stephen Hawking. Yeah, we lost a giant of physics when he died. But anyway, so now let's get to this question, what is the universe made of? And here the answer is very surprising. Because if you take all the objects of our daily experience, your body, the chair that you're sitting in, the air that you're breathing, the walls around you, let's include the Earth and the sun, everything that we know about, all of that is made of atoms. Atoms are made of quarks. But all of that stuff adds up to only 5% of the content of the universe. So that is the weird thing that we have to deal with. So drawing it as a pie picture, we only know this yellow part, the ordinary matter in the universe, and we have to figure out the 25% that's dark matter and the roughly 70% that's dark energy. And they're completely different things, and the focus of my talk today will be the dark matter. So this is from the cover of my book, The Cosmic Cocktail. I also put in a recipe. So we have some relatively unimportant parts as far as the total content, like if you have a 10-ounce drink, 0.05 of an ounce stars. Where are the supermassive? A millionth of an ounce supermassive black holes. So no, the black holes are these big guys are not making up the dark matter. And so there's a number of different ingredients, and 3 ounces dark matter out of 10, well, more like 2.5. And an answer to the question, shaken, not stirred in the early universe. All these things bumping into each other all the time. So I wanted to tell you why we know that dark matter exists in the first place. At this point, it's an 80-year-old problem dating back to Knut Lundmark in 1930 and Fritz Zwicky in 1933. So famously, Zwicky, who's shown on the right here, yes, I guess he was quite a character. So he was looking at the Coma cluster, which contains lots and lots of galaxies, and he was observing how they move, some galaxy moving around the center of the Coma cluster. And based on the matter that you know about, you think you know how this galaxy should be moving, but instead, the galaxies are whizzing around the center. So the question is, why are they moving so fast? Well, if you put additional matter in there, then that speeds things up. The gravitational pull would speed things up. And so this is called dunkle Materie in German, or dark matter, as the explanation. So he was a Swiss scientist, also working at the same observatories as Hubble. Yes, he was apparently a cantankerous character. In his book, he called his colleagues spherical bastards because they're bastards no matter what direction you look at them from. So this problem first emerged in the 1930s. Oh, I have another funny story to tell. Shall I do it? Okay. So I was on this radio show called Coast to Coast, which it's a California show that when I was on the radio, it was 2 a.m. to 5 a.m. in the morning for me, okay? And it's a lot of truckers who are, some are extremely educated about science, but most of them are very interested in UFOs. But this, I don't mean to be rude, but it's just true. And so somebody called in, and oh, I'm trying to remember her name now. Oh, Barbarella. Her name was Barbarella, and I said, oh, hi, Barbarella. Well, it turns out it's Barbarella Zwicky, the daughter of Fritz, and she went on a tirade about how nobody listened to him when he proposed dark matter. And so my only answer was, well, we're listening now. But anyhow, it did take several decades for people to take this as seriously as we do now, and it was the work of Vera Rubin and Kent Ford in the 70s that absolutely clinched it. What they did is studied rotation curves of galaxies and found that they're all flat. So let me show you what that means. I'm going to go away from dark matter for a minute. I'm going to talk about the solar system. So what I plotted here is how fast the planets are moving. So here we have Mercury, Venus, Earth, Mars, So as you're moving to the right, you're moving away from the sun. And if you count, you'll count 10 planets. I was supposed to get rid of Pluto, but I added another one. Anyway, so the speeds of these guys follow this formula here, and the basic thing is if you had a more massive sun, then everybody would be moving more quickly. So this shows the idea, even though it has nothing to do with dark matter, about what is meant by a rotation curve. By seeing how quickly things move, you can figure out how much mass is in there. So one of the main people who made amazing measurements of planetary orbits was Tycho Brahe, who lost his nose in a duel and wore a gold and silver replacement. But he was a master of studying planetary orbits, and I'm never going to get to the science if I tell more stories, but shall I do it anyway? Yeah. So there was a debate, how he died. For a long time, I'd always heard he died of a burst bladder at a dinner with the king, because you can't stand up until the king does, so don't drink too much wine. However, there were some people who thought that he died of mercury poisoning from his student, Johannes Kepler, in which case the famous Kepler's laws should actually have been attributed to Brahe. So they dug him up not long ago, in the last couple decades. They dug him up and they measured the mustache hairs, and there was no mercury poisoning. So I guess he just drank too much wine. So let's get back to dark matter now. Rotation curves of galaxies act in the same way as the rotation curve of the solar system, in the sense that you can look at things moving around the center, and by doing that you can figure out how much mass there is in the interior. And so the measurements of Ford and Rubin, they saw that things, whoa, if this is how fast things are moving, and this is what was expected. As you move out from the center of the galaxy, things should slow down, but that's not what happened. Instead, they found things moving really quickly. So that means, again, there's some mass that's missing from our understanding. And if you put in the additional dark matter, then it would add up. Let's look at a picture of our galaxy, the Milky Way. If you look at the center of the galaxy, it's shown in yellow, but it's just so you can see it, is a supermassive black hole that weighs 4 million times as much as the sun. And then coming out from that, there's a pinwheel of structure. These are spiral arms, and that's where the stars are located, including the sun. So we can follow out here, and you'll see the sun. But if you take this whole structure that we call the disk and look at it sideways, that's only a tiny piece of the whole galaxy. And here's an artist's rendition of what the whole thing looks like. You have that spiral structure, but then it's surrounded by a giant sphere of stuff, and that's called a halo, dark matter halo. I don't know where the word halo comes from, but which is made of some unidentified mass. We call it dark because it's not giving off light. Now, since the earliest days of Zwicky and Lundmark, there have been many, many pieces of observational evidence, so most of us are convinced that dark matter is there. You see it gravitationally pulling on lots of things. So I wanted to mention a few more. One of the main ones, actually, is that where I showed you that peak at 1 degree in the cosmic microwave background. If you analyze the other peaks, you also have to have dark matter at the level of 25% of the universe. Here's another one, Einstein's lensing. If you have any type of mass at all, it will bend the light that is coming for example, from a star. You have light coming past some dark matter, and it gets bent on its way to our telescopes. There's no kink, okay? It's just my bad drawing. So for example, if you look at a distant star, as it goes by the sun, that light is bent as it gets to the Earth. And in the process, you will get multiple images. Here's the real star, but you'll get multiple images. So 2 images where there's actually only one star sitting here, but it'll look like there's one here and one here. There'll be multiple images, and they'll be sheared and funny looking. So that's what you're looking for. And there's an app created by a Michigan grad student which has the right equations for gravitational lensing in them. And you can do this, okay? So you can lens yourself. And my students did it. And they lens themselves more and more as you put more and more dark matter in the way. So turning now to real data. Wait a minute. Okay, turning to real data, this is from the Hubble Space Telescope. So you have, in this picture, there's a lot of lensing going on. I don't even know all of it, but there are bright, distant galaxies with dark matter in between those galaxies and us. And the dark matter shears that background light and gives you the multiple images, and that's exactly, you can see that going on here. And using a computer to reconstruct the mass that would create this behavior, you get something like this. Now, this picture is not the same data as the last one, but these are just the prettiest pictures. So this is the kind of thing that you get. So you reconstruct the mass and you see here, well, here are the individual galaxies sticking up in a cluster. But even in between the galaxies, all this other mass is there. So even in between galaxies and clusters, you have additional dark matter. Now, there's another famous object that gives us more evidence for the existence of dark matter, and that's called the bullet cluster. So in this guy, we think what happened is that you started out with two clusters that merged, well, they bumped into each other, and as that happened, the atoms got stuck. So if you and I bump into each other, we're not going very far, we're going to get stuck. So that's shown in pink. So that's gas that we see in X-rays. The dark matter, on the other hand, it doesn't have as many interactions. It's pretty weakly interacting, whatever it is, and it goes through, it keeps going, and you see that from lensing in blue. So this is pretty clear that there's two different types of mass here. The ordinary stuff in pink, and then the dark matter in blue, that they behave differently. I wanted to show one more reason that we know dark matter has to be there, and that's because otherwise we wouldn't be able to exist. So that's kind of a cool thought, that the light matter, which we experience every day, required the existence of dark matter in order for galaxies to form in the first place. So I've got a series of slides here where you start out with most of the mass in the universe is uniformly spread out, but there are some regions where you have a little extra mass, and those regions pull in more matter and so on and so forth, and they grow into galaxies and clusters. So what you're seeing here in blue, those are lumps of dark matter that are pretty uniformly spread out, but they're about to start clumping more and more as the evolution of the universe continues. And this is in a simulation. I should say this is not the real world, this is a simulation. But the final result very well matches what we see in the universe today. So these kinds of simulations teach us not just about the existence of dark matter, because otherwise this whole picture would fail, but it also teaches us about the type of dark matter. So I haven't talked about all the different pieces of observational evidence for dark matter. There's even some extra ones that I've shown in pictures here, but all of it is really based on the gravitational influence of dark matter. But we still don't know what non-gravitational interactions dark matter might have, and we don't know what it is. So in terms of this pie chart of the universe, we'd really like to understand the pieces of the pie. I think I'll just go ahead. Okay, so let's go on to this question. What is the dark matter made of? And I'll start out with what it is not. There's a lot of simple things you might think of. Hot gas, cool neutral hydrogen, lumps of hydrogen, rocks or dust. It turns out that all of these would have observational consequences that aren't seen. So a lot of these things were ruled out already in the 1980s. So what are the candidates that we're considering seriously today? There are lots of them. Rocky, I put your favorite at the bottom, the WIMPzillas, invented by Rocky and Dan Chung. Rocky's student and my postdoc. But anyway, so The ones that we would have really preferred would have been neutrinos, because we know they exist. We make them in particle physics experiments every day. In fact, the Fermilab accelerator outside of Chicago is coming up to be the study of neutrinos. So these, we know they're there, but they're problematic. They are too light. So first of all, that would have ruined galaxy formation, but actually we now know what their masses are. Their masses add up to give about 0.5% of the total content of the universe. And if you tried to make galaxies with them, it would be a disaster, because they're so light and relativistic, they would just stream right back out. So neutrinos don't work. I put here in red some of the young people in my group who work on these topics. Okay, so neutrinos won't work. So we have a lot of other candidates here that are very interesting. The top two are the WIMPs and the axions. And the reason I say that is because they have reason to exist beyond explaining dark matter. They're already in theories for other reasons. So they are not these particles were not invented by cosmologists. We took advantage of them. So I'm not going to say a lot about axions, but they solve a problem in the theory of strong interactions that hold your nuclei together. So they could very easily exist in these theories, and there's a very big experimental effort devoted to looking for them, including there will be talks on this subject at the American Physical Society meeting here. But I'm going to focus on WIMPs, because this is the subject that I've worked on the most. These are weakly interacting massive particles, and that name tells you a lot. So there would be billions of these passing through your body every second, and somewhere between one a day or one a month would hit one of your nuclei, but it's not knocking you over or killing you. They don't have most of the forces that we experience in our daily lives. They don't have anything to do with the strong nuclear force that holds your nuclei together. They don't have the electromagnetic forces that produce the starlight that we see, that is the main force in our daily lives. Yes, they feel gravity, but the question is, well, we know of 4 fundamental forces of nature. What if these particles do feel the other force, the fourth one, the weak force, which is responsible for some types of radioactivity? So if you make that postulate, that's why we call these things weakly interacting. And the masses would weigh somewhere between 1 and 10,000 times as much as a proton. So these WIMPs are interesting for several reasons. One is that they already exist in particle theories that are extensions of the standard model that we know about. And so supersymmetry, for example, predicts that for every particle we know, there is a partner. So for all the quarks, up, down, charm, strange, there are, well, you put a twiddle over the top for the supersymmetric version. And for the Higgs, there's the Higgsino. For the photon, the photino. So it doubles the particles that we know, and these supersymmetric partners are heavier than our everyday particles, which is why we don't have a lot of evidence for them. But of all these supersymmetric particles, they would decay down to the lightest one, the lightest supersymmetric particle, and that thing would be stable, and you could have a lot of that particular guy sitting around, and that is a candidate for WIMPs, weakly interacting massive particles. The second reason that we like WIMPs as candidates is because if you make this postulate that they have weak interactions, in the early universe we can calculate how many there were of every type of particle, including WIMPs, and then we can ask how many are left today, and the number comes out about right. So I'm going to tell you about searches for these things. So there are 3 main ways to search for them, and one is to use the Large Hadron Collider at CERN. So this is in Switzerland with I think these are the Jura Mountains in the background, so you can go skiing. And this is a ring that's 17 miles around. So the way it works is that you have two proton beams going in opposing directions, and they're accelerated to nearly the speed of light. Then they're controlled to interact at intersection points. It's an amazing process how this is done. So looking underground, so you have these beams traveling about 100 meters underground. And here we have some of the detectors, the ATLAS detector, the CMS detector, sitting at these intersection points where these collisions take place. So one of these experiments that is the ATLAS detector, and here I've shown Fabiella Gianotti, who is now Director General at CERN. Here is the detector. For people who haven't seen something like this, that is a person standing there. So this is really an amazing human endeavor to build something like this. It takes a lot of people. And here's Peter Higgs, and in front of another one of the detectors, the CMS detector. And you may have heard about the discovery in 2012 of the Higgs boson. So as far as particle physics go, we know that particles have masses, but you want to know where did those masses come from? And a lot of them got their masses from this Higgs boson and this discovery, this bump here at 125. The Higgs boson was discovered, and it weighs 125 times as much as a proton. Uh-oh. No, it's okay. So a second major goal of the LHC, now that they found the Higgs, is to look for dark matter, to look for supersymmetry. So one of the ways to do that is if you have these collisions of two protons, then bam, out come supersymmetric particles. And in a chain, they decay to lighter and lighter ones until you get to the lightest one. That would be your WIMP, and that thing escapes detection, so you'd have missing energy. You add up all the energy, you know how much energy went in. You add the energy of everything coming out, and there's some missing energy. And you could detect some of these chains from these particles down here as well. Okay, nothing seen yet. That's frustrating. We have to say it's very frustrating. So we hope it's coming in the near future. Now, the second way to search for WIMPs is to build detectors here on Earth. And there's one technique called direct detection. What happens here is that you have, there's billions of these things going through you every second. They're all over the place. So take advantage of the fact and put a detector in the way. So when a WIMP comes along, here's your WIMP. It scatters off of this nucleus. And so this nucleus gets a kick. It picks up a little bit of energy, and the trick is to detect that energy. These are really difficult experiments. There's not a lot of energy being given to these nuclei. Like I said, you're not getting bowled over. So the problem is the count rate is low, the energy deposit is low. Very difficult experiments. But that takes me to how I got into this business, and the answer is yes, the cosmic cocktail. I was at a conference, and this man, Andre Drukier, took us to a New Year's party. Now he speaks, he's gotten better, but he's Polish, but speaks English, French, German, and Polish all at the same time. So I think I was the only one who listened to him. But he told me about work he was doing with another scientist on ideas for neutrino detection. Well, neutrinos are weakly interacting particles. So then I'm not going to go through the whole history, but we arranged a visit for him at Harvard Center for Astrophysics, where I was a postdoc, and we did some work on this because the same mechanism works for WIMPs. So we actually wrote the second paper on this for how it would work for the WIMPs in the galaxy. And this is the three of us back then. And because of the calculations that we did, experimenters were convinced that they could build something. So there's now an enormous experimental effort. I mean, we weren't the only ones to do this, but anyway, so WIMP detectors have to be in underground laboratories because you have to shield from cosmic rays. So for example, this is the xenon experiment. It's underground. It's underneath the Apennine Mountains in this tunnel, and here's the detector. So this is one of these experiments that's being built today. So because of these, so we made the calculations and proposed that people build this, and at this point it's a worldwide effort. Even at the South Pole, there's experimental effort. So one of the things that we pointed out is, it's called annual modulation, which is, so the sun is moving around the center of the galaxy, and that means that we're moving into a wind of WIMPs. It's kind of like when it's raining, it looks like the rain is coming into your windshield. But then because the Earth moves around the sun, you expect the count rate to go up and down with the time of year. So you expect lots of, so if your experiment is seeing WIMPs, you should see a lot of activity in June and nothing in December. So this experiment, DAMA, that's also in the same tunnel, sees exactly the data going up and down with the time of year, and they have more than 10 years worth of data, and there's no question about it. They're seeing an annual modulation, but the question is, of what? So are these WIMPs, or is it, well, we don't, you know, it's a tough question for several reasons. One is that the experimenters will not release their data, and that engenders suspicion. And the other is that other experiments don't confirm these results. So I had to show this. So here we have the leaders of 3 of these experiments. Let's see, who is here today? There she is. So this is Juan Colliar saying he's the leader of Cogent, Rita Bernabe of DAMA, and Eleanor Preeley of Xenon. I'm a Spaniard caught between 2 Italian women. So the problem is, and this is an outdated picture, but it makes the point. So this is, you have to be below these lines these days. However, if that DAMA experiment were right, you'd be in this green blob. So this is how many events you'd expect, and this is the mass of the particles. So it looks like if you have to be below these lines, that DAMA is just wrong. However, it's complicated. Oh, and by the way, this is very out of date, so I don't have the latest xenon data on here. But anyway, it's hard to compare results from different detector materials because DAMA is made of sodium iodide, and these experiments are made of xenon, and they're completely different. So these are the problems we face, but I did want to show the fun that we have. So Elena's here again, along with one of the other speakers, Lisa Randall. And here we have Rick Gateskill, the Lux experiment. So the question is, how do we test DAMA if we don't trust that we can compare with other experiments made of different materials? It's apples and oranges. To put them all on one plot, you had to make detailed assumptions about the interactions. So if we don't want to do that, then somebody else has to build experiments made of the same material as DAMA, and that's what's going on. There are 3 different groups doing that, and this one, Cosine 100, has a working experiment, so we'll know within the next few years. I wanted to show some futuristic ideas. This is using DNA for dark matter detection. The idea here is that you have a very thin, nanometer thin layer of gold. So when a particle comes along, it hits the gold, and it knocks the gold nucleus forward into these strands of DNA. When the gold hits the DNA breaks, it falls down, you can collect it. But the distance between these pieces of the DNA here are nanometer, so you're getting amazing resolution, and you can go back and track where the gold came from, which is roughly the same direction the WIMP came from, so that gives you directionality of the particle. So the status at the moment is that George Church is a well-known geneticist at Harvard, and he has built some stuff that he's got in the freezer waiting for the physicists to kick into gear. But anyway, so the third way to search for WIMPs is indirect detection, which is searching for the products of their annihilation. I didn't say this earlier, but a lot of these are their own antimatter, these particles. So whenever two of them hit, they annihilate and turn into something else. So here's a picture of that. You have the dark matter particles bumping into, hitting one another. They annihilate and they turn in the end into neutrinos, gamma rays, and positrons. Positrons are the antimatter for electrons. Gamma rays are high energy photons. And there are experimental efforts to look for all three of these. So the neutrinos, this is an experiment at the South Pole. In some of these, I don't have it here, but the Eiffel Tower is about this big for comparison. So you're going down 2,500 meters underneath the pole. So drilling holes in the ice there was an amazing technical achievement. They have seen really interesting, very high energy neutrinos that have nothing to do with dark matter. So another way to look for these things is the gamma ray sky, the high energy photons from the annihilation. The Fermi satellite is doing that, and at the center of the Milky Way, there, you can't see it that well here, but there's an excess of gamma rays that could be from dark matter annihilation. So there's some hints from DAMA, from this Fermi gamma ray excess, and theorists have to look for models to understand the consistency of all the different experiments. But in the end, you have to have compatible signals in a variety of experiments made of different detector materials. So the last thing I want to talk about is a thing that I've been very excited about, an idea that we had called dark stars. So this is an idea that was proposed by the three of us here. That's Doug Spoliar and Paolo Gondolo and me. And the idea is that the very first stars to form in the history of the universe could have been powered by dark matter. So there would be no fusion yet. These are very, very early stars. They're really big. They're as big as the distance between us and the sun. But they're made almost entirely of hydrogen and 0.1% of dark matter. But the dark matter annihilation is a really powerful heat source. So these things can grow to become very large, 1 million times as massive as the sun. Very bright, 1 billion times as bright as the sun. So we can hope to find them in the James Webb Space Telescope. That is the sequel to the Hubble Space Telescope, and it should launch in the next few years. It's also fun to speculate what happens to these big stars when they die, and what happens is they would make black holes, which could be seeds for these supermassive black holes that are seen everywhere. So there's a good chance of detection from these many different approaches for the WIMPs. And I think I'm running out of time, so I'm going to mention very briefly the dark energy, which the only thing that we know is that matter, by definition, is gravitationally attractive. But this dark energy, on the other hand, is causing galaxies to accelerate from one another. The universe is accelerating. So it has some kind of repulsive, sort of anti-gravitational behavior that we don't understand. And both on the theoretical side, it's a very difficult problem. And on the observational side, it's hard to learn about the details of how this stuff behaves. So I have a joke about this, which is that in June 2011 at the World Science Festival in New York, the three of us were talking about dark matter. And these three guys were talking about dark energy. And I said the only true thing that we know about dark energy So I will at this point conclude, and I do have 8 copies of this book if anybody wants to sign one, and I have the order forms for the discounted copies that you can buy from Princeton University Press, because they're not outside anymore at this point. And so they asked me to do this. These 8 copies, $10 per copy. There's only 8 of them here, or order one. But I think I will stop there.
Thank you, Katie. We have time for a couple of questions. And if you have a question, there are 4 microphones that are spread around. And we will call you when you get to the microphone.
For the questions, it might be good to have the slides back up. They took the slides. Could you put the slides back up? Because I might need them for the questions.
Yes, there's a question there.
Thank you. All right. So I'm not a scientist or anything. I just watch a lot of YouTube. And I heard Neil deGrasse Tyson speak on dimensions and how also gravity is strong, but it's really a weak force, and somehow it diminishes over time. And so my question is specifically, would it make sense for one of the explanations for dark matter, like hypothetically, if gravity can bleed out into other dimensions, is it possible that there's matter somewhere else and that gravity is bleeding into our dimension, hypothetically?
Well, you brought up about 5 different subjects, but the if string theory is a correct description of quantum gravity, and this is something that would allow you to go back in time before the Big Bang, then that only works if there are additional dimensions in the universe in addition to the 3 of our daily experience and time. And it is certainly that people have thought a lot about the cosmology of these extra dimensions. So one of the possibilities is that dark matter, as we've described here, could be as a consequence of stuff that is physics that's based in the extra dimensions. But it would play a role exactly. For example, there are WIMP candidates that come out of some theories of extra dimensions. So yes, extra dimensions can have an important impact on dark matter, but exactly within the context of everything I described today. And you could even detect them in a normal way. The other possibility, as you said, is there are theories where you have gravity in the higher dimensions has a different strength than it does in ours. But again, that doesn't necessarily change this story. So I think I'll stop with that.
Thank you.
We'll take a question here and then over there.
Hi. I haven't even started my physics degree yet, so I'm sorry if this question is kind of basic, but I was just curious about why, because you said that particles with dark matter interact with the Higgs field. I was wondering why something could interact with certain bosons and not others, and also how can something only interact with something like gravity, which is the weakest of the 4 forces, and not with the other 3?
So we do have a fundamental understanding of all the forces other than gravity. So the way that electromagnetism works, for example, if you have an electron and a proton, they're oppositely charged and they're attracted to each other. But they do that by exchanging a photon, which is light. So so dark matter doesn't have that kind of interaction. It doesn't communicate with photons, which is why it doesn't experience the electromagnetic force. And we say this because otherwise we would see it. It would give off light. Then as far as the strong interactions go, so there are for each of, I'm not going to go through them all, but each of the forces has a mediator, a mediating particle. So electrons interact with photons. They also interact with, they also experience weak interactions, so that would be W and Z particles. So the postulate for WIMPs is that they do interact with W and Z particles, but not with the particles that cause electromagnetic or strong forces. So that's the postulate behind the WIMP. And the reason that we've gone in that direction is because if they had if dark matter had strong interactions or electromagnetic interactions, we would have found it a long time ago. So we just don't see it happening.
Yes.
I'm curious about your opinion of modified Newtonian dynamics.
Yes. So this idea of MOND has been around for some time. The idea is that instead of having dark matter at all, that somehow Newton's laws have to get modified. And this idea was proposed because it allowed another explanation of these rotation curves of galaxies. So it could look like things are moving too quickly as you move farther away from the center of the galaxy because Newton's laws are different out there. So the original idea was just that postulate, just try that. So then people started trying to write down actual theories, mathematical theories that would produce that. And basically those ideas have not worked. So the remaining versions require, in addition to, well, so the version of this today is called TEVIS, where you have additional, I won't go into the details, but you have to have dark matter plus other things that are proposed. So it actually ends up being a more complicated theory rather than a less complicated one. So the idea initially was very good for explaining the rotation curves, but it doesn't work for other things.
Okay, the far end.
So, based on the density you guys expect to see of these WIMPs, how come we don't see gravitational evidence on a smaller scale, such as in the solar system?
Well, in the solar system. Well, I was going to say that the sun, at our location in the galaxy, the motion of the sun around the center of the galaxy is already being sped up by dark matter. So we're moving faster than we would be if the galaxy had no dark matter. But that's as far as the sun moving in the galaxy. Now, in the solar system, the numbers turn out to be small, irrelevant. So you can't use the solar system to test it.
Okay, we're going to cross the room one more time, and then Katie will answer them as you purchase one of her books.
I read Lisa Randall's book. I love to read that stuff.
She's giving a talk 2 days from now. Save your question.
Okay. No. This is about dark matter and dinosaurs.
Yeah.
She talks about the solar system going through a disk of dark matter that perhaps dislodged an asteroid. What's happened with that idea?
Okay, so there's an experiment called Gaia, which is measuring the movements of stars inside the galaxy. And by watching how stars behave, that tells you about where the dark matter is, if dark matter is controlling the mass. So if you want to look for a disk, well, we know about the disk of stars. That's the thing I showed with the spiral structure. But then is there a thick disk of dark matter? And as far as I know, there isn't. That the Gaia data shows that it does not exist. But please check with her.
Yes, a final question.
Hi, how's it going? I was wondering, in the beginning picture, when you show the Campbell soup of elementary particles, it showed that it seems to me that there are free quarks. And I was wondering, at what point in the universe did the quarks have to come in pairs, and if you have any insights on the mechanisms as why they have to come in pairs nowadays?
So in the early universe, it was so hot that quarks were flying around on their own. So there's 3 families, but there are 6 quarks. So up, down, charm, strange, top, and bottom. But they fit into 3 families. And as the universe cooled off, eventually these particles were able to stick together. Because if you had enough, let's go back to the really hot part where they were individual. Whenever they stuck together, then something would come along and burst them apart again. They couldn't make more complicated structures. But then eventually, you were able to make protons, for example. So a proton has 2 up quarks and a down quark. And that's one of the ways to make a particle. The other one is to have a quark-antiquark pair, like a pion. And that happened, the universe had to cool off quite a bit before that could happen. So that's our universe today. We don't have free quarks anymore in the universe today. In fact, if you take a proton, you try to pull one of those quarks out of there, the force is so strong that you're going to create an antiquark. So you'll have a quark-antiquark pair over here, and you'll get another proton. So you did have individual quarks, the very hot early universe, but not today.
Okay, Katie has agreed to take one more question.
I have a pretty basic question. What caused the Big Bang?
I told you not to take another question.
Rocky, you're the world's greatest cosmologist. Well, we don't know. The Big Bang is the limit of our knowledge. So as we go back in time, then we hit this cutoff in what we understand. And are scientists going to be able to do better than that? Yes. At some point, but not yet.
It's a subject for her to answer.
Yes, this is for your future.
Okay, thank you very much, Katie, and let's thank Katie for a wonderful lecture. Anytime. Boy, a lot of people to buy books here.
Yeah. Hi.
That's a very basic question. A very basic question. You said we got to. We didn't.